This is a problem walkthrough of limits using trig identities, and it's asking us to find the limit of theta as it approaches pi halves. Now, it's a good habit to do direct substitution here on your denominator to see if it's equal to 0, but since we know that this section with trig identities, they do equal 0, so our purpose here is to manipulate and use the identities to change that denominator to give me another value. Okay, so let's take a look here. We have tons of identities, and where to start. Now, I've gone ahead and boxed in the first identity that we're going to use here. And I know it's not cotangent squared, right? But if you think about this here, cotangent squared. So cotangent squared theta, all we're really saying is cotangent theta times cotangent theta. That's all I'm saying. So we can apply the same concept to this identity here. Cotangent, and let's make it a square, theta is equal to cosine squared theta over sine squared theta. Again, I'm using that identity. And based on math principles that we know already, cotangent squared is just cotangent theta times cotangent theta. And if it equals cosine cotangent theta equals cosine over sine, then we can just multiply it and or square it. Okay, so let's continue here and substitute cosine squared theta over sine squared theta, this portion right here, and let's substitute it for this. And it will look like this. Cosine squared theta again, let's just rewrite this. And all of that is being divided by 1 minus sine theta. I believe I already forgot. Yes, 1 minus sine theta. Okay. Now, this looks like a horrible division by division. So let's clean this up a little bit, and let's do keep change flip is usually the method I like using, or a way I like teaching it. Well, we keep the numerator, we change the division sign to a multiplication, and we find the reciprocal or flip of the denominator. So again, we're going to keep the denominator, or sorry, keep the numerator. I'm going to multiply now, and I'm going to find the reciprocal of my denominator, which is going to be 1 over 1 minus sine theta. Let's continue to clean this up a bit by multiplying them, and then you get cosine squared theta times 1, and then give myself a little bit more room. I have sine squared theta times 1 minus sine theta. Okay, that looks a lot better, but still not where we want to get to. So I am going to look at my numerator there, cosine squared theta. Now, I can see, and with practice you'll be able to see it a lot better, but I can see that I'm going to have to use the Pythagorean identities over here, right? And I'm going to use this one by subtracting sine squared theta to both sides so that we can solve for cosine theta. So if we subtract here, and we subtract it from both sides, we end up with something like this. One minus sine squared theta, because all of this that I just wrote is equal to cosine squared theta, and that is being divided by sine squared theta times 1 minus sine theta. So the reason why I saw this and I was like, oh, it looks like we're going to use Pythagorean identity, is because I look at this factor here, 1 minus sine theta. Okay, that looks like a factor of difference of squares. And that's exactly what I have here. Okay, so difference of squares states that if you have a term that's squared minus another term that's squared, hence the name difference, subtraction, of squares, and I have two squares, that's equal to the factor of a, factors of a minus b and a plus b. So in other words, we take the square root of my squares and then we rewrite them here in this form. Okay, so let's do that for my numerator, because I look here, 1 has a square, I have a minus, and I have another square. So difference of squares. So let's apply that here. My numerator will have, well, let's take the square root of 1, which is 1. Then minus b, okay, which is the square root of my second term, which is sine. And 1 plus sine theta. Okay, so that is my numerator now, through the difference of squares. Okay, and I'm going to rewrite the denominator. That looks a lot better. I can cancel these two out. Just becomes 1. And we're left with 1 plus sine theta all over sine squared theta. Okay, now can we check to see if we can do direct substitution now? Let's see. We were finding the limit as x approaches, or sorry, theta, speaking in terms of theta now, pi halves, okay? And that is 90 degrees, and that is sine, okay? Well, that looks like it's gonna work, because if we look here, 90 degrees, right, or pi halves, sine is my y term, and we have a 1 here. So as theta approaches 90 degrees, let's say, or pi halves, sine will be 1. Okay? So if we were to write this, continue to write this out, and let's say equals, we have 1 plus sine pi halves, and then we have sine squared pi halves. And we've stated that it's my y value, which is 1, so let's rewrite that and say 1 plus, then sine would be 1 all over, I'm really kind of just saying 1 squared, which is equal to 2 over 1. So my answer, or my limit, is at 2.